Okay, welcome to third week of the lectures of robotics. On the board you see a configuration of two consecutive joints of a Revolut robot like the Puma 560. You have here, and this is a schematic in defining the Denavit Hartenberg parameters. You will recall that we have four parameters, AI minus 1 here, or A, alpha I minus 1 here, DI here, and YI, or theta I. So you have two translational and two rotational parameters. You will see that different textbooks and different presentations may have some slight modification of these parameters. In order not to confuse you, we will stick to this one. And later on, I'll show you what your text is saying. Your text has this one and another one. So, in AI1 is the distance of the normal on Zi minus 1 axis and Z axis Z on that. Okay. Let's see whether I can get a better. This is a bit too small.
It says laser point. On the top? The top?
Oh, this one, laser point. Okay. Yeah. So this distance right here is AI or AI minus 1. Doesn't matter where you refer it to. But what's important that it lies on the x-axis right here. And this angle is 90 and this angle is 90. So as the two axes are imagined in the three-dimensional space, one is one way, the other one is another way, the normal between these two is the A. Okay. And which corresponds to the x-axis. Alpha I is the angle that you need to rotate around Zi minus around the x-axis in such a way that Zi minus 1 and Zi are coincide with each other. So let's look at alpha I. Alpha I is the amount of rotation around the common perpendicular, which is the x-axis, so that the joint axes are parallel. So if you have two axes like this, and then you rotate, it becomes like that. Two parallel axes. Now, once you identify this distance and you rotate, next thing you want to do is to move translation. And then you go to DI to line it up with this. So you come here, then you move AI and you basically make these two parallel. Then you move the axis DI, which is this, the displacement along the Zi axis, which is this axis right here, needed to align AI minus 1, which is XI minus 1, common perpendicular to the AI common. So here is AI, you move DI to coincide AI minus 1 and AI on the same direction, At that point that you have moved, and you moved it to move one higher in this fashion, the next thing you want to do is to have this additional rotation, YI or theta I, the amount of rotation around the Zi axis, to align XI and XI minus 1 together. So basically, you want to move the center, the coordinate of Zi minus 1 in such a way that the place where all the axes meet coincide with the Zi, the other one, and so forth and so on. So, as you can see, corresponding to these 4 DH parameters, there will be 4 transformations. Some rotation, some translation. So, having said that, the result will be a matrix like this, which constitutes sines and cosines of theta I, which is yi in that figure, and alpha I. And then, of course, you have di and ai, which are distances, and you can always expect them to be on the 4th column, because they are the end effector position in x, y, z coordinate. So the end effector is ai minus 1 in terms of x coordinate minus sine of alpha I di y coordinate, and similarly for z coordinate. So now I want to leave this set of slides and now take you to your textbook, and we will go to, let's say, here around 145. This is chapter 7 of your book. Okay. This is robot arm kinematics, chapter 7. And the slideshow I showed you coincides with this chapter. Now, these are 2 famous robots. On the left is the Puma 560 robot, which was the first robot built in this country and the world. Okay, in the 1960s, early 60s. And this is the Stanford arm, you see here. As you can see, a Stanford arm has a rotational around the base. It has pitch, yaw, and roll on the end effector, and it has a prismatic motion. The robot arm goes in and out. Okay. In some other varieties of original Puma, Stanford arm, a company called Adept, which are the offshoot of Unimation, when Unimation was sold to the French through Westinghouse. Some of the engineers in Unimation set up their own company in California. Adept robot is something you can Google it. I should have probably found a typical Adept configuration. I used to have one of those back in my other university. It has a prismatic joint, and it also comes down and out. It's excellent robot for VLSI and chip design and chip manufacturing. Okay. Unlike Puma or ABB nowadays, which are very good for auto industry and steel industry and so forth. So now, this is the diagram you saw before in the slideshow. However, it's different than in the following sense. That you have A as before, normal to the 2 axes, but you have D and theta on this side and alpha on the other side. Okay. I want you to basically just learn one of the configuration, and that's the first one in the slideshow. So don't worry so much about this. But what happens is the following. Typically, you have, as you can see here, you have a rotation around the z of theta I, followed by a translation along the z of d, followed by a translation along x-axis of aj magnitude, and then ended up with the rotation. The configuration that you saw in the slide is the opposite of this. Okay? But the answer, the following answer comes out anyhow, and that is typically what we call DH matrix. Okay? And corresponding to these 4 DH parameter, theta is the joint angle, the angle between xj minus 1 and xj axis about the zj minus 1 axis. It's a revolute joint. It's a rotational value in radians. Then d sub j is called link offset. The distance from the origin of frame j minus 1 to the xj axis along the zj minus 1 axis. If you look at this diagram, that's what that is. Okay, offset moves along this axis. And then the next one is AJ, which is called link length. As you can see here, this is the length from here to here. See, the same vertical, the same normal is also from here to here. So that regardless of the orientation of the two axes, the normal between these two doesn't change. It's consistent. And it's also called length of the length J. So length J is the same as AJ. Okay. Then finally you have link twist, alpha J, the angle from Zj minus 1 axis to the Zj axis about the Xj axis. That's the last translation, transformation, I should say. Now, traditionally, you also have this delta J. Delta J is the joint type. And you will see that two of them are here. When it's 0, it's a revolute joint, but all the joints are moving in a circular fashion. If it's 1, it's prismatic joint, which goes in and out or up and down. In a few minutes, I'll show you another chapter of another book which is on the blackboard, a rather old book, but it was somewhat fundamental. You can see more other joints also, besides charismatic and revolute. Okay, and now the nice thing about the author is that it also carries a history of robotics along the discussion of the concepts, and it also introduces you to the robotic toolbox as we go along. Okay, so as you know, next Tuesday and 2nd of February, I will be out of the country. However, Dr. Benavides will lecture on Linux and Python, and then robot operating system the following Tuesday, which I'll be back myself and I'll take part as an audience in the class. So we will have the next 2 lectures will be that. After that, Mr. Brad Roll will talk about the robot toolboxes. Not just robotic toolbox, but also maybe fuzzy logic toolbox, some of the other toolboxes which you could use to combine it with the control toolbox that I assume most of you already know from your control courses or systems courses, as well as apply it to the robotics application. So what is missing in the lecture, the way I would want it, is in introducing these robotic commands, explaining the concept that the author has described, is hiding behind all those concepts how complicated the problem is that he very professionally programmed it and put into a toolbox. For example, inverse kinematics, I'll show you 12 nonlinear simultaneous equations today, which you have to find 6 unknowns out of it. And that's a very, very difficult problem, as you know. And infinite solutions, and unacceptable solutions, many different things. But those are not in your book, but it's in another book which you have access to it. And I'll go visit those books and come back. So this is Professor Hartenberg, who was for many years a professor at Northwestern, and actually Denavit was a Frenchman who actually was a graduate student of Professor Hartenberg, and was born and raised in France, And the two together in the mechanical engineering department of Northwestern, they came up with this notation, which now pretty much accepted all over the world. Okay. Now, let me tell you what, here's the forward kinematics issue. Forward kinematics is the multiplication of, this is that N-link robot. You have the Denavit Hartenberg matrix from base to end of link 1. From link 1 to link 2, link 3, link 4, all the way to the end. So if you have a 6 degree of freedom Puma 560 robot, or a 6 degree of freedom ABB robot, which you can do experiment in it, you have 6 of those matrices have to be multiplied. Now remember, each of those A matrices themselves is the product of 4 matrices, those 4 parameters and translation and rotations of their own. Remember that? I showed you a list of those. So you're talking about 6 times 4, 24 matrices are multiplied here to go from base to the end effector. That's the forward kinematic. It's not very difficult because all you need to do is multiply a bunch of matrices. And that's what MATLAB does perfectly. Okay. So this is forward kinematic problem. So let's look at the tooling robot. Okay. It is very difficult to teach from this course and keep ignoring the toolbox. It's everywhere. Okay. So for a tooling robot, something like this, you want to do a forward kinematics, you just basically write a Denavit Hartenberg transformation for this link at this point, and then this you multiply together. That's all you need. And then once you multiply together, you see the last row, the end effector is at 1.707 in the x direction and 0.701 in the y direction. And in the z direction is 0, which means the robot is planar. It's on plane. It's not in 3D. Okay? That's what that's. You will learn all of these things. You see, FKINE is the forward kinematic command in MATLAB. Okay? By now, I hope that you already have downloaded the latest version of the Toolbox. You know, if not, you'll see a slide of how to do it. Then there is a specific forward kinematic for tooling, which says tooling.fkin, where the first link rotates pi over 4, and the other one minus pi over 4. Okay, and then you can see it right here in the 3 dimension on the toolbox. This is the home location, the base of the tooling robot. And then when you have a pi and a minus pi, it looks like this. Okay? And even show you a shade of the robot, okay, on the floor. Okay? So you just say tooling plot, and it plots this for you. Tooling plot, pi over 4 and minus pi over 4 and so forth. Now for a 6-axis robot, you're going to have 4 of the DH parameters are going to be constant, because once you build the robot, every joint after each other, the distance between the 2 successive axes are fixed. That's 0.4318 for the first to second, and 0.0203 for the third one, and then you have here the last part of the robot, the end effector. Alpha is also in radians and fixed. D is also fixed. The only variable is the theta, is the rotation of the joint. Okay, the base moves, the shoulder moves, the elbow moves, and then you pitch your and roll. Okay, that's, you have 6 of them. Okay. So here is a Puma is a cartoon of a Puma 560 in different configuration. Okay, and you can plot this easily. Now let me see inverse kinematic is just the opposite of basically this notation, equation 7.5, this C, this Greek letters C. If you look at the nomenclature of your book, and I strongly have you take a look at those pages, beginning of the book, because there are 3, 4, 5 pages of nomenclature in the book. If you want to know what that means, you can go to nomenclature and it tell you that. And what that is a pose, P-O-S-E, pose of the robot. You have end effector like this. End effector has a 3 axis here and has an orientation in this direction. Okay. And if you want to pick up an object, you need to know the coordinates of the object, and you have to program your robot to move exactly to that location to be able to pick it up. Okay. So Q is the vector of all rotational angles of your let's say 6 degree of freedom for that particular pole. This is the equation where it has infinite solution. Because as you will see in another book by Professor Fu and Professor Lee and others out of Purdue, which was the first book which I used to start teaching robotics from in 1980s. It still has a lot of value. So instead of explaining to you how complicated this equation is, they immediately go to the toolbox, and you miss the point as a scholar and a student to actually be able to appreciate that it's a very complicated problem. Okay, and I'll intend to walk you there in a minute. So the key for this particular is the inverse kinematic is IKINE6S, one of them. So you have here QI is P560.IKIN and T, where T is the basically the pose of the robot. Okay, this tells you that the robot is located at -0.596 for X, -0.1504 for Y direction, and -0.0144 in the Z direction. And orientation, you have to basically, this is given as a final configuration to you. It's the whole thing is given to you. So, in fact, what you can see, what you have done is the following, that you can type in, you start with an angle, theta 1 all the way to theta 6. You give it to the forward kinematic, it gives you the pose. You give the pose to inverse kinematic, see what you get the angle back. Okay, that's what's good. Okay, to get that. Sometimes you may or you may not get it back. Because remember, it's one of the infinite solutions. So this is what it is. You get this from forward kinematic right here, FKINE. You give it to the inverse kinematic and you get this angle, which is not the same as what you had before. You see what I mean? It's not the same as before. So anyhow, then you can plot them and look at them and so forth and so on. So let me, to appreciate the enormity of the problem, I will take you to chapter 2 of the book, which is in this book is actually it should be on your blackboard, is chapter 2 of Robot on Kinematics Fu et al., F.U. et al., late Professor Fu of Purdue University.
It's in Dropbox.
It's in Dropbox.
Dropbox
It's not on
Blackboard.
Okay, thank you. So it is in Dropbox that you can download it. And let me try to repeat some of those concepts in this book. The DH transformation representation, again you have these 4 parameters, theta, d, a, and alpha. And here is a complete schematic of a Puma 560 robot. Here is the base, here is the shoulder, here is the elbow, here is the arm or the end effector. And you have 0 to 6. You will have basically 7 coordinates. But the last one, 6, is actually coordinates in the Cartesian space. It's the one which is attached to the object you're trying to handle. Okay. Imagine that I am a 6 degree of freedom robot, and this is an object in the 3D space. The 6, x, y, and z. 6 is sitting on this object. Up to here is number 5. Okay, and you put it. So here is the robot arm coordinate parameter. This is the table I mentioned last time that it comes with the robot. When you order a robot, this table comes with it. And in this particular configuration, they're like this. Everything is fixed. But as you saw a few minutes ago, in reality, for a Revolut robot like Puma or ABB, this theta is always changing variable. Everything else is fixed. This is the configuration of the Stanford arm. The Stanford arm, you see, has a revolution here, a revolute here, and then you have a motion like this. So a Stanford arm is basically has a base like this and has an arm which goes extension of the arm, and it goes all the way down and then goes down. And then you can move around in 3Ds. Okay. So you have 3 motions here, one around this, and one here. This also is 6 degree of freedom, where 5 of them are revolute, 1 is prismatic. So what they have done in order by being able to rotate this axis here, that robot, that arm can, or that extension can go down and up. You don't have to have an additional motion to move in and up and down. You see what I mean? That's perfectly all right. And this is the particular DH table. So now let me see how I can. Okay. So for a typical DH matrix that you saw a few minutes ago in the slide and in numbers in the toolbox, going from joint I to joint I from I-1 to I, you have this DH matrix. And as you saw before, in order to get the forward kinematic, you have to keep multiplying them one after another. Typically, you have cosine of theta 1 minus sine of theta 1, because there's so much mathematical values in trigonometric values. C corresponds to a cosine, S corresponds to sine. Now sometimes you may have, later on you see, when you multiply them together, you get C1, C2, 3. What is that? That means cosine of theta 1 times cosine of theta 2 plus theta 3. That's what that is. A2 times cosine of theta 1 times cosine of theta 2, and so forth and so on. So this T1 is transformation matrix from the base to the third joint. And then this T2 is from third to the sixth one, just before it goes to the real world, to the Cartesian space. Now, if you multiply these two, you get forward kinematic. Okay? And this kind of representation you don't see in your textbook. Okay? The textbook is good to, with the help of the toolbox, for you to appreciate solving a problem and being able to verify it, hopefully in the lab. So let me stop here. We take a few minutes and then we'll come back.